Chapter 6.1, our intention on 6.1 is to find the area between curves. If you remember back in Chapter 5, we used integrals to find the area between the curve and the x-axis. And now we're going to find the area between a curve and another curve. And it's basically the same idea. What we did in Chapter 5, imagine that if we found the area under f of x, from f of x to the x-axis would be this right here, right? Like so. So if we did the Chapter 5 technique on f of x, we would get the area of all that blue stuff. And if I did the Chapter 5 technique on g of x, finding everything underneath g of x, would be all this green stuff, in a little bit of yellow where I didn't get the blue. All right. If I take f of x, which is everything under f of x, to the x-axis, subtract g of x, which is everything under g of x, what's going to be left is the black shaded part, which is the area between the curves, right? Does that make sense? So what we would have done in Chapter 5 would have been the integral of f of x dx would be the blue part, right? And the integral of g of x dx would be the green part. And if I subtract those two integrals, I would get the area between the two. And if I have the subtraction of integrals, that's the same as subtraction of the functions as an integral from starting at a and going to b. One other thing that's going to happen quite often in this is they're going to give us boundaries, x equals number to x equals number. Recall back from Algebra 1, x equals number is just a vertical line. All right, so if x equals a and x equals b, they're just telling me the end of beginning ending. Another thing that happens quite often in these problems is you graph them. Let's say one graph does something like this, and the other graph does something like that, and they want to find the area between the curves. We have the ability to find points of intersection, so the area between the curves would just be this. So if they don't give us the endpoints, that's because the graphs themselves intersect more than likely. We'll have to find that point of intersection. So that's basically the idea of all the problems in this section. They're going to be find the area between the two curves. They may or may not give you the endpoints. Sometimes graphing is helpful. Calculated graphing is sufficient usually to be able to see what's going on. So, example 1, find the area of the region bounded above by 10 minus x squared, bounded below by x plus 1, and bounded on the sides by x equals negative 1 and x equals 1. So the word bounded is going to be used quite often. If you have a region, just to give you an idea, y equals 10 minus x squared looks like that. It's a parabola. Y equals x plus 1 looks like that. It's a line. Bounded above by 10 minus x squared, bounded below by x plus 1, bounded on the sides by x equals negative 1, x equals positive 1. When they talk about a region, they're talking about some area, some space that's being taken up by all these things. So if it says it's bounded on the top or on the bottom on the sides, that's all it's talking about. The top part is this, the bottom part is that, the side parts are these. As far as graphing this would be concerned, if I was to graph this on my calculator, it looks like this. y1 equals 10 minus x squared. y2 equals x plus 1. I'm not going to put x equals negative 1 and x equals positive 1 because my calculator doesn't work that way. It doesn't have x equals, right? The way I get x equals negative 1 and x equals positive 1 is by set my window, start at x equals negative 1, end at x equals positive 1. Okay. If I'm starting at negative 1, ending at positive 1, I've got the boundaries on the sides, right? Taken care of. So, and as far as the scale, it's not really that matter. It doesn't matter that much. As far as the y scales, y min and max are concerned, if I don't want to put any thought into it, maybe negative 10 to 10. Hit graph, see what happens. Yeah, the blue graph represents the top. The red graph represents the bottom. Okay, so, and that kind of, I mean, it doesn't look exactly the same because of the scaling, but, you know, it has that idea. It looks like it doesn't get below 0, so if I go back to my window, maybe go y min 0. I get a little bit more detail on our graph. There you go. So what they're asking me to find is how much area is in between the blue and the red from negative 1 to 1. All right? So, I'll just cover that up. There we go. Much prettier. So all we have to do is we have to construct an integral to represent this. And the rule says that the integral starts at the lowest x value, ends at the highest x value, so from -1 to 1. So anytime they give me side boundaries like this, all that's doing is just giving us the interval for that integral. And I'm supposed to do the top integral minus the bottom integral. The top integral is the blue, which is 10 minus x squared. And the bottom integral is the red, which is x plus 1. One thing to be cautious of here is quite often your equations are going to be multiple terms, and there's subtraction quite often in these problems. Subtraction in multiple terms, make sure there's parentheses around this second one. And the last thing I'm going to do before I actually integrate this is actually simplify it as much as I possibly can. Combining like terms, distributing, and all that good stuff. I'm going to get negative x squared minus x, and then 10 minus 1 makes plus 9 dx. So if I evaluate that integral right there, that should represent the area between the two curves. The integral of negative x squared is negative x cubed over 3. The integral of negative x is negative x squared over 2. The integral of 9 is 9x. Going from -1 to 1. And as we should know by now, all that means is to substitute 1 first, then -1 second, subtract the two evaluations. So if I put 1 in first, I'm going to get -1/3 minus 1/2 plus 9 minus, and if I put -1, I'm going to get positive 1/3 minus 1/2 minus 9. -1 cubed is -1, negative makes it positive, -1 squared is positive 1, negative keeps it negative, and -1 times 9 makes -9, right? So all together, looks like common denominator 6 going on here, so I'll go ahead and make that happen. -2/6, that'll be -3/6, that'll be positive 54/6, that'll be -2, that'll be positive 3, and that'll be positive 54. The minus sign distributes through, changing the signs of each of those. -3 plus 3 cancels. 54 and 54 is 108, minus 2 and 2 makes -4. 104 over 6. And that reduces by 2 down to 52/3. 52/3 would be the approximate area, or the exact area, I should say, between the two curves. Alright, this is what I'd expect to see on your paper. Again, using your calculator to graph them to get a feel for what's top, what's bottom. That's the main thing. If you construct the integral properly, you should create the correct work here that's going to get you the correct answer. That's kind of what I'm looking for in each of your problems, that I would see this on your paper. I don't have to see a picture of the graphs. I can believe that you can look at a graph on a computer screen or calculator screen in order to establish a top